All right, let's look at one more example of a frame or machine. This one, I've got another horizontal member on a pin. Kind of a theme there, isn't it? Got a horizontal member on a pin here, stretches out quite a ways. We'll say it's going to be 8 meters, which seems unreasonably long, but that's what we're going to call it. So 8 meters, right in the middle, you've got a pin and an applied force straight down of 7 kilonewtons. Again, 8 meters, so that means 4 meters from each side. Okay. And then we've got vertically, just a simple vertical member. We'll say it is 3 meters from the pin right here in the middle down to the bottom of that. And we'll pin this end over here. And a member connecting those two ends there. And then we're going to say that right here, kind of in the middle of that, we're just going to put a roller. And that roller is going to be on a surface parallel to this member here. Right, being 4 horizontal, 3 vertical, so we'll have the same thing here. This is going to be 4 horizontal, 3 vertical on this surface here that I've got a roller on. And so we'll label these points here so we can talk about the same thing. We'll say that's A. B is this point right here, this pin right there in the middle. C is this pin right over here at the very end. E is this pin down here at the bottom, and we'll call this D, point D. Now, the problem wants to know, find the horizontal and vertical components of the pin forces at A and B. So that's what we're looking for. Again, 7 kilonewton applied load right there in the middle of ABC. Pin at A, roller at D. Find forces here and find forces there. All right, well, a variety of ways we could do that. We can just go right ahead and find, oh, by the way, you need to know this horizontal distance right here from point D to point C is 2 meters. And what that does is it tells us this is right in the middle of this member. Because it's 4 meters long. Well, it's 4 meters horizontally. And 2 meters horizontally to where that roller is. So that puts that roller right in the middle of that. Okay. So, if we draw a free body diagram of the entire structure, I'm going to go to the next page to do that. I got just barely not enough room to do it on the very bottom. Let's go to the next page. Free body diagram of the entire structure. L13, page 5, page 6. This one's page 6. Probably going to be page 6 of 6. I think I can get it done a page. Free body diagram of the entire structure. And that will give us all of the reactions. So just a simple diagram of this structure. We've got AX, AY. I can almost hear you yelling at me that you can't see it. I apologize. 7 kilonewtons. And then I've got this normal force at D It's perpendicular to this surface being a 4 horizontal, 3 vertical. I know some of you guys are still trying to find the angles in here. I don't care about the angles. It's a waste of time. If it works for you, go for it. I shouldn't say it's a waste of time. If it works for you, that's fine. This is, again, 4 is horizontal, 3 is vertical. We're going to be perpendicular to that. So if 4 is horizontal, that means on the perpendicular, on the normal. 4 is going to be vertical. 3 is going to be horizontal. I don't care what the angle is. I just know this is a 3, 4, 5 triangle. So 3/5 is going to be the horizontal component. 4/5 is going to be the vertical component. Those replace the sines and cosines of any angles. Distances, 4 meters horizontally over to where that 7 kilonewton force is. Again, we said this is 2 meters from this edge, so that means it's 2 more meters from this edge, and so that's the distance I'm going to define here, because I'm probably just going to take moments about point A to get here. I do also need to know that the whole thing is 3 meters vertically, and this point D is right in the middle, so it's 1.5 meters from the top or the bottom to where that force D is applied. That becomes handy when I do a moment equation. Okay, which I might do right off. Let's say sum of moments about point A equal to 0. In fact, I'm just going to let you pause here, and I'm going to pause and go ahead and get your reactions. All right, it strikes me this one's a little bit more difficult than our normal pin roller situation, so I went ahead and showed us some detail here. I'm a little warm and I'm a little tired, so I'm not thinking very good. I apologize. I mixed up my equations, but I'm confident in these values. If you get something different, please put them in the comments. Now, let's talk about what is it that we're trying to find now, right? What do we want? How does this help us? Well, it does help us in that these are 2 of our answers. What are we looking for? We write that at the very beginning so we can go back to it. What am I looking for? I'm looking for vertical and horizontal components at pins A and B. So I've just found, because A is just a simple reaction for us, so I've just found AX and AY. So those are 2 of the unknowns I'm after. Now I need to figure out, how do I find vertical and horizontal components at point B? Okay, well, there's a few things you could do. I might say, well, you could draw then member ABC, but you would have 4 unknowns if I do that. I've got BX, BY, and CX, CY. Now there is a trick you could employ here. I'm going to show us how to solve without seeing it. If you see it, you feel free to go ahead and pause right now, work it through with the simplification trick, and then go ahead and then play this video and see if your answer matches. There is a trick that I could just draw a member ABC and solve right now. Again, if you got it, pause and then come back and watch this at like double speed so you kind of see if you did okay. But if I don't see the trick, then I've got 2 unknowns here and I've got 2 unknowns there if I draw a free body diagram of this thing. So I can't do that right off, or at least I wouldn't be able to solve it. I could do it, wouldn't hurt anything. I just wouldn't be able to solve it right off. Okay, well, what could I solve? If I drew this guy from C to E, if I drew this one, I know this value now. I found D, so I could solve this guy. So let's do that. Let's draw a free body diagram of CDE. If you want to pause it here and draw your free body diagram, that's what I'm going to do. Just pause it, see if you can draw this. This one's a bit complex. All right, this is what I've got. I move these distances out here to not interfere with the EX and EY. Again, this is the first time I'm seeing these pin forces, so I'm going to draw the positive side of the pin first. Go ahead and see if you can solve these equilibrium equations. Go ahead and pause it, see if you can solve this. Okay, did you try to solve it and realize you can't? You can't actually solve it because I've got 4 unknowns here and I can only write 3 equations, so I can't actually solve it. So Steve, what the heck are we trying to do? Well, that's a good question. What I can do is I can maybe put CX and CY in terms of each other by taking sum of moments about point E And if I know Cx and Cy in terms of each other, then when I go back and draw this free body diagram, I would know Cx and Cy in terms of each other. I'd have an additional equation that I could then solve this free body diagram. So that's what I'm going to do. And you could write sum of forces in x and y if you like. This is what I'm going to do. I'm going to say sum of moments about point E equals 0. And go ahead and write your sum of moments about point E here. All right, this is what I've got. So again, about point E, both x and y components of D are going to cause moments. Both of them end up being a counterclockwise moment. Cy is also going to cause a counterclockwise moment at 4 meters, and Cx is going to cause a clockwise moment at 3 meters. So now I've got Cx and Cy in terms of each other. So I've got one equation involving both Cx and Cy. I could write 2 more equations here if you like, but I don't know that it's going to help us because, again, all I really want to know is what are these pin forces at B? And I can write 3 equations from this free body diagram. So let's do that now. And now I've got one more equation to bring to the party. So I'm going to go ahead and start one more sheet of paper. It's actually page 7 for this lecture. Okay. So if I do that now, if I draw a free body diagram, yes, Izzy, we are busy. Free body diagram of A, B, and C. So I've already found AX and AY. You can put those values in here if you like. We found those earlier to be 4.31 kilonewtons and 1.26 kilonewtons. Now the question might come up, hey Steve, why don't you draw those in the opposite direction? This is the second time you've drawn it. Because, that's a very good question. Why am I drawing these positive when normally the rule is you draw them negative, right? Well, notice back here, because this is the same side of this pin. I'm not drawing the opposite side of the pin, which is just the wall. Right? I'm not just drawing the wall. That would be the opposite side of the pin. I'm still drawing this right-hand side of this structure, the side that's attached to this member here. So it's the same forces in the same directions. And I solved those earlier to be positives here. So I'm going to leave them as is because, again, I'm drawing the same side of the pin. I'm not drawing the opposite side of the pin, so I don't need to draw them opposite. Now, we've taken apart point B here. There is the 7 kilonewton load force being applied. Now I'm taking apart the pin at B, and it's the first time I've taken it apart, so I'm going to go ahead and draw those two positive. But now I did draw this side of pin C earlier, and I drew these two positive. So since I've drawn these positive, and this is actually Newton's third law, for every action there's an equal and opposite reaction. So here I need to draw the opposite of those, because I've already drawn them positive once, and I already have an equation based on them being positive on the other side of this pin. I need to draw their opposites on this side of the pin. That's the reason we flip those, is because, again, here I've drawn basically the left-hand side of the pin. This is the right-hand side of the pin, so to speak, or the opposite side of the pin, so therefore those forces are now opposite. Distances, we need to know 4 meters and 4 meters. And again, remember I've got this equation from earlier. You should be able to solve this now, right? I should be able to, with this fourth equation, I should be able to write 3 equations here. And ultimately, I'm just after bx and by. So you should be able to solve those now. So go ahead, knock it, and pause it, see if you can get to a solution. All right, let's see how you did. So any number of ways you can solve for these 4 unknowns, again, with this equation involved. This is what I did. I took moments about B. That gave me Cy, because Cx doesn't cause a moment. Or actually, no, I guess I started out, I took moments about C. If I take some moments about C, that gives me By. So taking some moments about point C, I can find By, because Bx doesn't cause a moment. By becomes my only unknown. So that's what I did. This is what I got for By. And then I took some moments about B. If I take some moments about point B, CY becomes the only unknown because CX doesn't cause a moment there. So I can find CY that way. So I've got BY and CY now. So given that, again, remember, we said earlier, we've got this equation from our other free body diagram back here. So if I employ that down here, so now I know CY. I plug it into this equation I had earlier. Solve for CX. I find CX to be 4.31 kilonewtons. And then, if I look in sum of forces in the x direction, I've got this. I now know this. This is my only unknown. Solve for that unknown, and notice what happens. I've got the 4.31 kilonewtons coming from A. I've got plus BX, and CX is in the negative direction, and I found it to be 4.31 kilonewtons, so it's minus, this is CX. So minus CX, or 4.31 kilonewtons. These cancel out. BX is equal to 0. And we need to look at that and say, hey, whoa, does that make sense? Should BX be 0? Remember earlier I said, hey, there's a trick. What do we know about this guy? From B to E. Notice there's no forces being applied to this member BE. BE is a two-force member. That means the only way BE can be in equilibrium is if all of the force runs along its axis. So that means BX, or E, both E and B have no X component because the member is in the Y direction and there's no other forces applied. Notice you didn't have to see that right off. You can show that mathematically. That's typically the case, and that any problems I give you, that would be the case. If you saw it right off and said, hey, Steve, I know BX is 0, I can solve this free body diagram because now I've only got 1, 2, 3 unknowns, and we didn't have to go through this whole page. We found we could find AX and AY here, and then I didn't have to go through this process, right? Because you could have looked at this and said, well, BY has to be 0 because BE is a two-force member where the forces only run in the Y direction. So BX is 0, BY is the only unknown there. Now I've got one free body diagram. I can write 3 equations, 3 unknowns, and I can solve that. I could have gone right to here after I found my reactions. Okay? All right, and seriously, it's okay. That's like advanced level. If you don't see that right off, that's really no big deal, but I did want to point that out. All right, so we got all our answers. A little over 15 minutes, so I'm going to stop the video here. Let me know what you think. Questions, comments, complaints.